Hello, everyone. My name is Jakob, and today I'll be talking to you about the implementation of phase field models for brittle fracture in Code Aster. So first of all, a little bit about our research group. I'm a research assistant at Aarhus University, Department of Civil and Architectural Engineering, and we are a group of 8 people in Giuseppe Abbiati's research group. And we do a lot of work in structural engineering, different areas such as nonlinear system identification, multi-body dynamics, and finite element analysis. And also this work couldn't have been done without the help of Simvia, and in particular also Brittle. Today I'll be talking about phase field fracture, and I'll briefly present the main ideas behind this method. And then I'll show you 2 ways to implement phase field fracture in Code Aster. And in between them, I'll just expand the theory to a micromorphic approach, which we'll use for the second implementation method. And a few disclaimers before we start. So these are implementations that can be done without modifying the source code of Code Aster. And also the second implementation method allows for models that are more general, so not just those for brittle fracture. But in any case, let's start with phase field fracture. I'm going to try to answer 2 main questions in the beginning. What is phase field fracture and why use phase field fracture? So first of all, what is phase field fracture? It's a way to do computational fracture mechanics and a way to do it with a continuous formulation. So the way it describes fracture is with the damage variable D, which is 0 for an intact material and 1 for a fully broken material. So we can consider a discrete crack in 1 dimension. Then this damage variable or phase field variable would look something like this. But in the phase field approach, we would like a smooth damage field varying between 0 and 1. So instead of a discrete crack, we can consider a diffuse crack instead, in which case the damage variable would look something like this. And this is the main philosophy of phase field fracture, is that we approximate these discrete cracks by diffuse. In a finite element formulation, we can consider a general finite element where we have the displacement degrees of freedom at the nodes. In this case, we would add a scalar damage degree of freedom at each of these nodes. Okay, so that was what is phase field fracture. Why should we use phase field fracture? There are some advantages. I've listed some of them. The main advantage is that we have an implicit crack representation. So that means we do not need to explicitly track the cracked interfaces. And also it has a very simple extension into a 3 dimension. We can handle complex fractures such as cracks branching or merging quite easily. Of course, there are also some downsides to phase field fracture, mainly that we need a fine mesh to resolve the crack, which can cause a high computational cost. Let's look at the equations to phase field fracture, because this is what we need to implement and solve using Code Aster. So phase field fracture has 2 governing equations, which are coupled partial differential equations. We have a mechanical equilibrium equation, which looks like this. It's quite standard, but we have this more non-standard relationship between the stress and the strain, which also depends on the damage. And then we have a damage evolution equation, which is this rather long expression, and it comes with an additional constraint, which means that the damage or the crack is irreversible. And if we try to break down this equation, we have the first part, which is the crack resistance. Then we have the second part, which is the crack driving force. And then we have also an inequality in this equation. And basically it means that the crack resistance can be greater than the driving force, or it can be equal to the driving force. And if it's greater than the driving force, then we don't have damage evolving. And if it's equal to the driving force, then damage is evolving. We also have this y, an internal variable, which is usually known as the effective driving force. And then we have to enforce the damage bounds. And basically we can implement different phase field models by varying some of these parameters in the damage evolution equation. And today I'll mainly focus on the AT1 and AT2 models. So let's look at how we can implement these equations in Code Aster. In general, phase field fracture is a multi-field problem, so we have two coupled PDEs we need to solve. And we can do this with a monolithic scheme, so where we solve for the fields simultaneously, or we can do it in a staggered scheme where we solve for the fields separately. And in the case of phase field fracture, we have the unknown fields, the displacement field, and the damage or the phase field. And the monolithic scheme has shown to have convergence issues, whereas the staggered scheme is generally more robust. So this is also what we have implemented in Code Aster. And the phase field fracture staggered scheme can be broken down into two main problems we need to solve. We need to solve the mechanical subproblem, and we need to solve the phase field subproblem. So for a specific time increment, we can initialize the unknown fields to solve for, and then we can start the iterations where we first solve for the displacement field with a frozen damage field, and then we solve for a damage field with a frozen displacement field, and we basically just keep iterating until we hit until we get convergence. And then of course we update the current results and we increment the time. So this is the main solution scheme that's implemented in the Python interface of Code Aster. But let's dive deeper into how we actually solve these subproblems using Code Aster, because this is the main problem of this approach. So first of all, let's look at a bit of the characteristics of the subproblems. So we have the mechanical subproblem, which is a quite standard elasticity problem, but we have this non-standard constitutive law. So the stress depends, as mentioned before, on the strain, which is decomposed from the strain energy density, and also the damage. So this constitutive law we can implement using mfront, a code generation tool for mechanical behaviors. And this is coupled natively in Code Aster. And for the phase field subproblem, we have a less standard damage evolution equation, but we can use a thermal analogy because the structure of the damage evolution equation is similar to that of the transient heat equation. And I'll talk more about this in a bit. And also we have this inequality, so we couple Code Aster to PET-C in order to use a bound constraint solver. Let's look at the thermal analogy. On the left we have the transient heat equation, and on the right we have the damage evolution equation, specifically for the AT1 model. And this is in continuous form. We can also see in the spatially discrete form. We have these similar structures between the equations, except that we have the time dependence in the transient heat equation. But in any case, we can obtain the analogy if we set the thermal parameters equal to the corresponding parts of the evolution equation, and then we can consider the spatially discrete heat equation. But instead of having this traditional equation, we augment it, so we solve this equation instead, which becomes equivalent to solving the original damage evolution equation if we consider that the temperature and the damage are equivalent. So this is the main analogy we use to solve this damage evolution equation. And this is specifically for the AT1 model, but we can also do it for the AT2 model with different expressions for the thermal parameters. So finally, let's look at the flow for implementing this in Code Aster. So we have the current displacement field, which we input as an initial state. And then we have the material parameters and the current damage field, which we input in the material field. And these are used in the nonlinear static solver, which is coupled to mfront for the behavior integration. And this is basically what solves the mechanical subproblem. And as an output, we get the updated displacement field, and we get this effective driving force Y, which is then input into the phase field subproblem, along with the material parameters GC and L. And according to the thermal analogy, these are used both in the source term and in the material field. And we can use these to assemble the global matrices and then solve this augmented equation using the interface with PET-C, subject to the constraints that we have, that damage cannot be reversed. And the output of this is the updated damage field, which we then input into the mechanical subproblem in the next iteration. So far so good, but if you've worked with Code Aster, you also know that a field is not just a field. It has a physical quantity, and it also has a discretization. So let's try and take this into account. So the output of the mechanical subproblem is the displacement field located at the nodes, which is fine because this is also what we need to input as an initial state. The effective driving force, on the other hand, is an internal variable field located at the element Gauss points. And this can cause a problem because we cannot input this as in the material field of the phase field subproblem. So we need to configure this driving force. And we go from the internal variable field located at the element Gauss points to a neutral field still at Gauss points and to a neutral field at the element nodes. And this we can use as an input in the phase field subproblem without losing any information. And the same for the updated damage field of the phase field subproblem. This is a temperature field located at the nodes because we use this thermal analogy. And we also configure this damage field into a neutral field located at the nodes. And this is what we input in the mechanical subproblem. So this is the main flow of the implementation in Code Aster, all done in the Python interface. So let's look at some results. I have 3 test cases today. A homogeneous specimen, which is basically a single finite element, which we can then compare to an analytical solution. Then we have a notched specimen subjected to shear, and then tension, and then we have a notched specimen subjected to shear as well. And for the tension and shear specimen, we also compare the results to Phoenix. And these are the results of the simulations. In the top, we can see the damage fields, a uniform damage field for the homogeneous case, and a localized crack in the tension and the shear cases. And in all 3 simulations, we can see that the correspondence between Code Aster and Phoenix is quite nice. We've also compared the performance, and this is mainly to show that even though we can implement phase field fracture in Code Aster, it may not be the most efficient way to do it, at least with this thermal analogy. We can see that at least the simulation times in Phoenix is much shorter, but Phoenix might also be a more suitable tool for this kind of problem. This was the first implementation method of phase field fracture in Code Aster. So now I'll briefly expand on the theory to a micromorphic approach, which we'll then see how we can implement in Code Aster. The main objective of the micromorphic approach is to make the phase field, or the damage field, a local quantity. And the way we do this is that we regularize the problem with the gradient of alpha, a new field, the micromorphic field, instead of the gradient of d, the damage field. And then we basically enforce that the constraint that alpha should be equal to d so that we obtain the original problem. So visually, in the original formulation, we had the displacement and the damage field at the nodes. And now in this micromorphic formulation, instead of the damage degrees of freedoms, we now have the micromorphic degrees of freedoms at the nodes. And we move the damage to the Gauss point, so it becomes an internal variable field. This changes the governing equations as well. We still have the mechanical equilibrium equation, which is unchanged from our previous formulation. But now, instead of a damage evolution equation, we have a micromorphic evolution equation. And this is a new equation that we need to solve. The structure is not really the same as before. The first part is similar to the gradient term we had before. And the second integral is because we have this constraint that we enforce alpha to be equal to d. We can also look at the internal variables we now have. So we still have the same stress measure. We also still have the same damage driving force. But now we also have the damage as an internal variable. And we can obtain it by, at each Gauss point, we basically solve this equation subjected to the constraints that we have. And the main advantages of this micromorphic approach is that we now have a governing equation which is independent of the phase field model, and we also have the constraints on the internal variables. So we no longer need a bound constraint solver for this problem, but we can basically use minimum and maximum functions to enforce these constraints locally. So let's see how we can implement this micromorphic model in Code Aster. A micromorphic model can also be seen as a non-local model with an internal variable gradient. And this might ring a bell for some of you because this is already implemented in Code Aster with the modelization grad vary. These are the equations that are solved with grad vary. And if we have the micromorphic model as a reference on the right, we can see that they're actually very similar if we consider this non-local parameter c equal to this the same expression on the right, and we consider the internal variable a in the grad vary formulation to be the damage. There's a few notes on this grad vary implementation. So first of all, we still need the mfront to update our internal variables, so to update the stress and to update the damage. We are required to use P2 elements for the displacement field. So basically, instead of having this formulation, we add some additional nodes with only displacement degrees of freedom, but this does not cause any problem for us. And finally, what could cause a problem is that it's a monolithic solution scheme that's implemented in Code Aster. And if you remember in the beginning, I said that this could cause convergence issues for phase field fracture. So to overcome this and to get convergence for such a simulation, we use a path following method, which helps this convergence problems. We have the same three cases for verification. Again, we compare against the Phoenix X, and we can see, so just as a quick note, the implementation in Phoenix is not a micromorphic model, it's the original phase field model. And it also doesn't use a path following method, it uses basic displacement control. So this is why we don't have an exact correspondence in the force displacement response, but we can see that the responses are actually quite, they fit quite nicely. And we can see that the cracks for both the tension and the shear specimen also matches what we saw earlier. We've also looked at the performance for this implementation, and of course we cannot compare directly Code Aster and Phoenix, but in this case we can see that it actually seems like Code Aster, the implementation in Code Aster is much more efficient. Also taking into account that it has many more time steps because of this path following method. In conclusion, I've shown you 2 ways we can implement phase field fracture in Code Aster. The first method was use a thermal damage analogy, a staggered solution scheme, and a bound constraint solver. And we saw robust convergence due to this staggered solution scheme, and it preserved our original phase field formulation because we had this damage field located at the nodes. But because we use this thermal analogy, it limits the phase field models that we can actually implement. And we also saw that the simulations were quite slow. The second implementation method used this grad vary micromorphic analogy in combination with a monolithic solution scheme used with the path following method so that we could get convergence. The advantages of this method is that the phase field model is at a constitutive level, so we can basically implement new phase field models by not by changing the governing equations, but by changing the constitutive relationship. And then we can enforce the constraints locally, so we don't need a bound constraint solver. The disadvantage of this method is that the monolithic scheme is not robust by itself, and the path following method, at least the one we chose, is maybe not ideal for this kind of case because it uses a lot of time steps to get the full response. Thank you for your attention.
Thank you very much for the very nice talk. It's a very impressive work that has been done. And I have a question regarding the implementation details. Did you use, the capability of Code Aster to transfer the fields between Code Aster and PETSI? We can convert now fields and matrices, and you can play with this object, using parallel simulation We will be talking about that in the afternoon. And
yes, we did use the native capabilities of Code Aster to convert from the Code Aster matrices to the PET-C matrices. So we basically had for, let's say, the stiffness matrix, we basically just used this to PET-C function to obtain the PET-C matrix. Yeah.
I have also a question regarding the use of the SNES nonlinear solvers. You use them outside Code Aster because now we have a new nonlinear solver, which is called Mecha Nonliné, where you can use directly a SNES solver.
No, we used it outside of the, yeah, but we have looked into maybe using the new functionalities. But for now, we've used it outside of Code Aster. So yeah, we basically made the function calls to assemble the matrices used for the PET-C interface.
Thank you very much.
Thank you for this presentation. I don't know if I missed a point, but I have a question about the result of the second, the second trial. I saw like a drop in the force displacement, a drawback.
Yeah.
Can you just explain what it is? Yeah.
Which part are you talking about?
Like the tensiles, like the middle one.
Okay, so the drop in the force displacement is because that's where we have the crack evolving.
Yeah, but why we have a drawback, not like we have a reduction in the force at the same time reduction in displacement. Did you force like your conversion?
So you're talking about the snapback?
Yeah. Yes, exactly.
So this is also a part of the way the phase field method works. So there's a big snapback in the beginning, which is, it can have something to do with the way you introduce the initial notch. So the way we do it here is with pure geometrically, so without phase field boundary conditions. And if you do it, which maybe not be the ideal way to do it, I think if you do it in a more appropriate way, so also use phase field, so boundary conditions for the damage, we do not see this snapback. But for comparison between Code Aster and Phoenix, it does not really matter because we see the same response both in Phoenix and Code Aster.
Thank you.
Thank you for the very interesting presentation. Do you think you present quite rather simple test case, which is quite long in terms of calculation times? So how do you think that the phase field approach could be competitive with other approaches in the future, like for instance, I don't know, XFEM for propagation or things like that? Do you think that the calculation time could be improved to be applied to industrial problems?
Yes, there are many things that we can do. So this is this does not use, for example, MPI parallelism, which would really help this kind of simulation. But this is because it's mostly preliminary results, and you can also use. It's very common to use what's it called, adaptive meshing methods, so that you adaptively resolve the mesh as the crack evolves. And this is also not something we've implemented yet. But there are many methods that could really speed up these simulations. Yes.
Thank you very much. But in this schema, it's very difficult to obtain the solution by numerical approach. Can you take more detail about your algorithm using to converge in this snapback solution?
Can you repeat this? Sorry?
Yes, algorithmic schema using for criterion to stabilization your...
So what we do to obtain convergence in these cases?
Yes.
So for the first implementation method with the staggered approach, it's actually very robust, and it doesn't really need any additional tricks to obtain convergence. But if you keep iterating between these two subproblems, it can take a lot of iterations, which takes a lot of time, but at some point you will get the convergence. For the second method, we used a path following method to limit the maximum strain increment in an element. And this was something that we also had to play around with to see what parameters would actually work for this kind of problem. But in this case, the automatic time stepping of Code Aster was also really relevant because it really helped the convergence. Because if the time step was too large, it would automatically decrease the time step.
I ask, is that better to using the energy approach?
Sorry,
Energy approach.
I don't.
Yes. You say about using the equilibrium approach in your algorithmic system, but for my opinion, it's better to using this energetic approach.
Energy approach.
Yes.
We haven't
It's
really
the combination between combination and forces and displacement together.
we haven't really considered that.
Okay. Thank you.